in IMPA. And he's going to talk about the geometry of surfaces in three-dimensional homogeneous spaces.
Thank you very much. I'd certainly like to thank Marcos for having a birthday and being responsible for all these great talks and all the good people who I'm talking to here. I'd like to say a word of encouragement to Marcos because he's now 60 years old. I was 60 years old a while back. And it wasn't at all clear to me that after 60 you could do good mathematics. Now I think definitely you can do good mathematics after 60. But maybe some of my friends say, oh, poor Harold, his judgment is so bad now that he's so old. So, you know, you never know, but it's important that you think that it's good, right? Anyway, happy birthday, Marcos. I'd like to talk about surfaces in three-dimensional manifolds that are homogeneous and Riemannian submersions over two-dimensional space forms. So M2 of kappa is going to be the two-sphere of curvature kappa. Kappa is positive. R2 of kappa is 0. And the hyperbolic plane of curvature kappa when kappa is negative. This Riemannian submersion will also have the property that the unit tangent vector field tangent to the fibers, C, will be a killing field. The orbits will be geodesics, and it'll be a killing field. Now, we can think of these, what are these manifolds? I think of kappa as positive, kappa 0, kappa less than 0, tau equals 0, tau different from 0. There's one other condition that I'm going to impose on the relationship between kappa and tau, that is that kappa minus 4 tau squared is different from 0. To say this is 0 gives the space forms, the three-sphere of curvature kappa, hyperbolic space of curvature kappa, or R3. So we're going to suppose that this is never 0. When kappa is positive and tau is 0, we have a product space. We have the two-sphere of curvature kappa cross R, S2 cross R. Kappa 0, tau 0, well, it's R2 cross R, it's R3. Doesn't count, it's not on our list, so this is empty. Kappa less than 0, we have the hyperbolic plane of curvature kappa cross R. Tau different from 0 and kappa positive, we have Berger spheres. When kappa is equal to 4 tau squared, when this is 0, one passes through the three-sphere of constant curvature. Kappa equals 0 and tau different from 0. This picture is not big enough. We have Heisenberg space. Neal 3. So this is R3 submersed over R2 with the metric that I'll describe a little later. And here, when kappa is less than 0, we have the twisted H2 cross R, which is PSL2R tilde. The universal covering space of PSO2R, which is also the universal covering space of the unit tangent bundle to the hyperbolic plane.
What is tau?
Tau is a real number. Kappa is a real number.
Tau is the curvature of the bundle?
Tau is the bundle curvature. Okay, let me talk about the geometry of these spaces. Okay, so why am I talking about these spaces? What's the point? After the space forms have a isometry group of maximal dimension equal to 6. And after the space forms, the next most symmetric spaces are these spaces whose isometry group is of dimension 4. One has translation along the vertical fibers or isometries is a killing field. One has rotations around each fiber, that's 2, and one has horizontal translations, which are killing fields as well. So one has a 4-dimensional isometry group in these spaces. They're homogeneous. We have an isometry taking one point to the other. So these are homogeneous spaces that are the most symmetric possible after the space forms. There's one other space that should be mentioned, and I will talk about, and that's solve 3, whose isometry group is of dimension 3. So this is a Lie group. It has 3 one-parameter groups of isometries coming from left translations in the Lie group. It does not have rotations. That's what's missing here. It does not have rotations. So this is, we'll see what this is geometrically and topologically in a moment. But if one takes solve 3 plus these spaces minus the Berger spheres, one gets Thurston geometries. The Thurston geometries are precisely E of kappa tau minus Berger spheres union solve 3 union the space forms. Any 3-dimensional Riemannian manifold is built up from building blocks isometric to one of those 8 manifolds. So these are very homogeneous manifolds, and that's not the reason I got interested in them at all. Why did I get interested in these manifolds? I'm interested in minimal and constant mean curvature surfaces. And one of the things that has been very difficult during my whole career in that subject is finding examples, proving existence theorems. And then the next thing after that is proving unicity, that the example you found has certain properties which make it unique. And just before I became interested in this subject here, I was trying to solve the following problem, which is still not solved, which is to give you some idea of what I just said. And the problem is this. Consider a 3-dimensional Riemannian manifold whose sectional curvature is bounded away from 0. So it's a 3-sphere with a strictly convex metric. And take some number h, constant, greater than or equal to 0. Find an embedded sphere sigma in n of constant mean curvature h. Constant mean curvature h. So I thought this problem would be easy, and I tried and I tried and I tried, and lots of people have now tried. The problem is not solved. We do know something about it. We know it's true for h equals 0. A student of Leon Simons named Smith did this in his thesis. And we know that it's true for h very big. This is a consequence of a theorem of Ye, who, in any Riemannian 3 manifold, looked at a critical point of the scalar curvature function, point P, which is a critical point of the scalar curvature function, and showed that you can foliate a neighborhood of this by constant mean curvature spheres. So the h is very, very big. So for h very big, you know the answer to that. H equals 0, you know the answer to that. And in between, one doesn't know anything. Now this problem, I thought, well, what if I go down 1 dimension? Maybe this will become much easier. Going down 1 dimension means look at the 2-sphere with a metric of positive curvature. So consider N2, the 2-sphere with a metric of positive curvature. And ask the same question now one dimension less. Take a number C, I'll call it C. Does there exist an embedded Jordan curve whose geodesic curvature is constant equal to C? This is not known either. Just as difficult. 2 months ago, a very beautiful paper was posted on our by Schneider. And let me just mention that Antonio Ross and I proved that this is true if you accept Alexandrov immersed circles. So if you consider Alexandrov embedded, then it's true for any C. However, up until 2 months ago, all we knew is that for C equals 0 it was true. This is the theorem proposed by Poincaré, but without a complete proof. And for C very big, it was true. The same kind of construction as Ye's theorem. But Schneider, with a very beautiful geometric idea, if the curvature is 1/4 pinched, then it's true. Any C, you can find an embedded Jordan curve on the surface of curvature equal to C. And if you want to see a very nice geometric argument which relates various things, just look at this paper of Schneider to understand why 1/4 pinched enters into it. It's really a delightful argument. Okay, so this is the kind of thing that it was easy to state, very difficult to deal with, etc., etc. And I just happened to look at S2 cross R years ago, and then H2 cross R. And I realized that one can construct many, many examples of surfaces that I found very interesting. Minimal surfaces, constant mean curvature surfaces, many, many more such surfaces than in R3, where I had spent years and years studying surfaces. In H2 cross R, you have much richer structure of minimal surfaces, constant mean curvature surfaces. Let me just give you one simple example. I'm not going to really talk about many examples today, but to give you one example of a minimal surface in H2 cross R, and then we'll go on to talk about some of the theory in this subject. What is the standard way of constructing minimal surfaces in R3? One of the nicest ways is take a polygon, compact polygon, a Jordan curve, solve the plateau problem. You get, if the polygon is chosen appropriately, you get an embedded disk, minimal disk. And then do Schwartz reflection around all the sides. And if the polygon is chosen appropriately, you'll get a complete embedded minimal surface in R3. Right? You've seen constructions like this. So the easiest thing to do is take a polygon like this, solve the plateau problem. Now let me just point out that this choice of the polygon, this solution is actually a graph over the rectangle that it projects to. It's the graph of a function u that satisfies the minimal surface equation in the interior, not on the boundary. But then you have this, you can do Schwartz reflection to reflect the surface. It continues analytically across. You can keep on going. And Schwartz did this to construct his triply periodic minimal surface for appropriate choice of an initial polygon. But let me point out to you, when you do this in R3, initially this is a graph. Next time it's also a graph. So you can extend this graph. Well, it's not a graph here, it's vertical here, but you can extend this to the other side by this reflection. You get another graph over this domain. When you do these reflections and you come underneath this, then it's clear there'll be a vertical line meeting the surface in at least 2 points. So you're never going to get a non-trivial graph or entire graph by this process. And we know there's no entire minimal graph in R3. That's Bernstein's theorem. But if we do this in the hyperbolic plane, then we get a entire minimal graph that's non-trivial. So that's the only example I want to point out. One other remark about the isometry group of these homogeneous spaces. So as I said, there's a four-dimensional isometry group. Rotations about the vertical fibers and translation along the vertical fibers and horizontal translations. There's a discrete subgroup of the isometry group that's very important for what we do in this subject. If I take a horizontal geodesic, this is a horizontal geodesic with this reminding in submersion, then there's an ambient isometry which is rotation by pi about this horizontal geodesic. That's a fact about all of these homogeneous spaces. Discrete subgroup of the isometry group. So you have these rotations by pi. If I take a vertical geodesic in this space, I have rotation by pi around the fiber. This is the vertical. So it makes sense to look at polygons in, for example, H2 cross R, composed of horizontal geodesics and vertical geodesics. Solve the plateau problem and do the symmetries. So if I imagine the hyperbolic plane here, you could imagine taking 4 geodesics, putting boundary values 1, 1, 0, 0, solve this problem here. So here it's the same picture as this, but now the geodesics. This is a geodesic. And you get a graph here, U, which takes these boundary values. If you work a little, you can see that these points can be made to go to infinity, and these minimal graphs will still exist. That is, we can take an ideal quadrilateral here. Let's take it regular, for example, so I get a nice tessellation. And I can find the minimal graph with these boundary values, U. Now do the rotation by pi about this horizontal geodesic. This extends to the other side. And the boundary values are 2, 1, 2. And keep on going. Keep on going. You get an entire minimal graph. Entire minimal graph. So this is just a simple example. If you think about this example, it has very interesting ergodic theory, dynamics. If you take a geodesic on it and you ask, where does the geodesic go when you get to infinity? What's the behavior of it? What are the values on the sides it takes? There's a very nice ergodic theory in just this simple example. Now, in S2 cross R, one can construct examples also of any genus G that are properly embedded minimal surfaces with one top end, one bottom end. That's easy to do by this kind of technique. It's easier to do than in the three-sphere, the way Lawson did it. It's really simpler to do. So one had all these examples, and one can start studying them and proving theorems. And a few years ago, I was visiting IMPA, and Marco said to me, Harold, Abresh is coming to IMPA next week. Do you mind talking to him? So Marcos is responsible for what I'm going to talk about now. Marcos was unable to talk to him that week. So, okay, well, what's the point? What's one of the theorems of classical differential geometry that we know? It's the theorem of Hopf concerning constant mean curvature immersed spheres, or the Hopf holomorphic differential, which says that in a space form, you take sigma to be an immersed in a space form, an immersed sphere, constant mean curvature, then sigma is round. It's an embedded umbilical sphere. That's the Hopf theorem. How did Hopf prove this? It's really the idea of the proof that interests me here. So he looked at sigma, he looked at its second fundamental form. So suppose H sigma, second fundamental form. And he considered the 2-0 part of the complexification of this. So this is a quadratic differential QH. I'll define this in a second. The 2-0 part of this quadratic form. I'll need to tell you what this means because I'm going to do it in another context in a second. What does the 2-0 part mean? When one says this, one means with respect to the first fundamental form. There's something missing in this expression. This depends on respect to the first fundamental form, which I'll call the metric on sigma, the induced metric, G sigma. So what this means is the following. In the conformal parameter Z on the surface sigma, write the first fundamental form as lambda dz squared. Now you have this quadratic form here, the second fundamental form. Well, in this coordinate system, you can write the second fundamental form complexified, so I complexify this, just extend it as a complex linear map, quadratic form, as a combination of dz squared, dz bar, and dz bar squared. So you can write it as something q dz squared, complex function, plus it's 2h lambda dz squared, dz bar, the 1 part, plus q bar dz bar squared. By definition, the 2-0 part is precisely q. And this is called, right in this context here, the Hopf differential. Let me remark for the future reference an important property. If I take a quadratic form which is itself a multiple of modulo dz squared, then its 2-0 part is 0, identically 0. When you take this 2-0 part of something that's gamma times modulo dz squared, you get 0 by definition. So Hopf showed that this is holomorphic when h is constant. H is constant, h of sigma is constant if and only if this quadratic differential is a holomorphic quadratic differential. Holomorphic. This depends on the Cardassian equation in the space forms. And the real part of Q is the second fundamental form minus h times the first fundamental form. That's a little calculation. The real part of QH is the second fundamental form minus h times the first fundamental form. What was Hopf's second observation? On the 2-sphere, as a Riemann surface, any holomorphic quadratic differential is always 0. That's the only one you have on the 2-sphere. So this differential is identically 0. So the real part is 0. So the second fundamental form is a multiple, constant multiple of the first fundamental form. So it's umbilical, it's round. That was Hopf's proof of his theorem. Well, Abersh and I were looking at S2 cross R, H2 cross R, and it's easy to examine the rotational spheres of constant mean curvature in these spaces. They're not umbilical. So one can look at the differential equation. It's an ordinary differential equation. And you can sigma h, the rotational embedded spheres, topologically spheres, of constant mean curvature h. In, say, S2 cross R. And you look at the second fundamental form, and let me introduce some notation that will be useful for the future. Here I have the vertical tilting field. In this case, it's a product. It's just ddt. If I look at the tangent space of sigma at a point, this point, I have normal vector field, unit normal vector field, n sigma, and I can project this onto the tangent plane. I'm sorry. I can project this onto the tangent plane, and I get a vector t. So I write c as equal to its tangent part on sigma plus the angle function times the normal. So nu is the scalar product of normal and c. T is the projection of the vertical killing field onto the tangent plane. T, I'm sorry, thank you. Thank you very much. T plus nu times the normal. And since it's an orthogonal projection, the length of t squared plus nu squared is 1. So these are two important objects and surfaces in these homogeneous spaces. T, the tangent part of the killing field, and nu, the angle that the normal makes with the killing field C. The scalar product of n and C. Okay? Now, when you look at the rotational spheres, it's easy to see that the principal curvatures are in the vertical plane and the horizontal plane. So one of the principal curvatures is parallel, principal directions is parallel to t, and the other is just horizontal vector orthogonal to t. So then you calculate h sigma with respect to that t and its orthogonal, and in that basis the matrix h plus 1 minus nu squared over 4h, 0, 0, h minus 1 minus nu squared over 4h. So t is the principal direction, its orthogonal horizontal is the principal direction, and you calculate those to be the principal curvatures. So one observation when you look at this, if 0 is less than h is less than 1/2, it's not convex. And it's easy to see that as h goes to 0, this converges to a double cover of S2 cross a constant. Just collapse down. So they're not convex. They're not contained in a hemisphere cross R, so you can't do Alexander reflection. So the standard techniques to prove that embedded CMC surfaces in S2 cross R are rotational using Alexander reflection is not going to work because the spheres are not, won't fit into that technique. Well, what we calculated was, what does one have to add to H sigma to get a quadratic form whose 2-0 part vanishes on these rotational surfaces? What do you have to add to this quadratic form to, and a simple calculation, in this case, if you consider 2h times the second fundamental form, and add this correction term, minus dc squared, then on these rotational examples, this is a constant multiple of the metric. This is equal to a certain constant times g sigma. What is dc squared? Dc squared, this is the dc squared, it's the quadratic form. If I take two vectors x, y tangent to sigma, it's the scalar product of cx times the scalar product of ty. So that's dc squared. As I said here, when I define what the 2-0 part of a quadratic form is, if the quadratic form in question is a multiple of the metric, then its 2-0 part vanishes identically. Q is identically 0. Because this is the metric, so this vanishes and this vanishes. So therefore, the 2-0 part of this quadratic form vanishes on the rotational spheres. So the 2-0 part of 2h h sigma minus dc squared is 0 on sigma rotational, this sigma h. So then we got to this point, okay, that's the simplest term to add to that to make it vanish. Any chance it's holomorphic. This was in May or June, but it was Christmas time. We calculated it, it was holomorphic. So this led to the following theorem. Consider any sigma CMC immersed in E of kappa tau. CMCH. Constant mean curvature equal to H. And, okay, so, and consider the quadratic differential Q equal to 2 H plus I tau, this constant, times the 2-0 part of the second fundamental form of sigma. That's the usual Hopf differential. This 2-0 part is Q Hopf, plus the correction term, which is kappa minus 4 tau squared. And the space forms, this is exactly 0, so it's the Hopf differential, times the 2-0 part of dc squared, the vertical killing field. Okay, that's Q. What's the theorem? The theorem is that Q is holomorphic on sigma. So it's a constant, it's a linear combination of the Hopf differential and this dc squared differential with constant coefficients depending on kappa and tau. Then Q is holomorphic on sigma. Okay, why is this interesting? Well, we're able to prove this theorem. Again, it's aberration myself. Suppose you take a complete H surface in this homogeneous space. Complete H surface. Constant curvature H. Such that this quadratic differential is 0 on the surface. Then the surface is invariant by a one-parameter group of isometries of the ambient space. Sigma is invariant by a one-parameter group of isometries of the ambient space. This one-parameter group of isometries might be a solvable group, etc. In the case that sigma is compact, that one-parameter group is necessarily a rotational group. So in the case when sigma is compact, you know it's rotationally invariant. If sigma is compact, then it's rotationally invariant and embedded. No, I take that back. Forget embedded. It's not true what I just said. Rotationally invariant. Okay, now, come corollary of this, if sigma is topologically a sphere, there are no holomorphic quadratic differentials on the sphere except 0, then sigma is an embedded rotational sphere. So this proves the Hopf theorem in these homogeneous spaces. And it gives much more structure to understanding H surfaces in general, complete H surfaces immersed in these homogeneous spaces. Now, for those of you who are specialists in the subject, you know that in space forms, the Hopf holomorphic differential for H surfaces is a very important tool for understanding the surface. Sterling and Pinkel have classified, for example, CMC tori in R3 using this holomorphic quadratic differential as a basic tool. This enters into the study in S3 and in H3 of CMC surfaces. And this differential has been useful to understanding what's going on for H surfaces in these homogeneous spaces. Let me mention a very nice theorem in Heisenberg space, which was proved by Isabel Fernandez and Pablo Mira, which is the solution to the Bernstein problem in Heisenberg space. Let me just say some remarks about the metric on Heisenberg space. So there's a coordinate system called exponential coordinates such that Heisenberg space, I'll call H. So here, this is equal to E kappa is 0, tau is 1/2. That's normalization I'm taking. So it's R3 with the metric dx squared plus dy squared plus dz plus 1/2 y dx minus x dy squared. And it's a Riemannian submersion over the flat R2. dxy, the projection. If you look at the minimal surface equation for z equals f of xy in this coordinate system, the minimal surface equation for graphs, the equation one gets is 1 plus beta squared fxx plus 1 plus alpha squared fyy minus 2 f sub x, f sub y, excuse me, I'm thinking in terms of Euclidean space, minus 2 alpha beta f sub xy, identically 0. What's alpha and beta? Beta, in Euclidean space, beta would be f sub y. This term would be 1 plus f sub y squared. The correction term here is minus x over 2. And alpha is partial respect to x plus y over 2. So it's a variation of the minimal surface equation. However, this equation has many entire solutions over all of R2. So the Bernstein problem is to classify all entire minimal graphs in Heisenberg space. And this is what Pablo Mira and Isabel Fernandez did. What am I going to do? It's about 1/3, 1/4 of my talk. Okay, let me try and speed things up and not too much. So let's examples of this are this saddle type surface. That's an entire minimal graph. It solves that differential equation. You can add a real constant here times something with logs in it, which I wrote down. It's a complicated formula to get a one-parameter family of surfaces like this. Also, f is equal to constant, so the z equals constant planes are minimal. And the theorem Fernandez and Mira is the following. consider holomorphic quadratic differentials on the complex plane or on the unit disk. Look at holomorphic quadratic differentials Q on C or the unit disk, the open unit disk, with one exception. If on C, don't look at Q identically 0. Okay, so what they did was, to each such holomorphic quadratic differential, they associated a two-parameter family of entire minimal graphs, which is generically non-congruent in Heisenberg space, whose differential that Abersh and I constructed is the Q given. So first of all, given such a Q, there exists a two-parameter family of entire solutions, entire minimal solutions, whose holomorphic differential is Q. This is what they call the canonical family associated to quadratic differential. This is non-trivial to construct this family. They use the theorem of Wan O that says you can find, given such a quadratic differential, you can find a complete H equals 1/2 surface in Lorentz space, Lorentz 3 space, which is space-like, and whose Hopf differential is Q. The Gauss map of that differential is a harmonic map to the hyperbolic plane. Using Q and that harmonic map to the hyperbolic plane, they construct this two-parameter family using a theorem of Benoit-Daniel on when you can find surfaces in these homogeneous spaces. So that's the first part of the theorem, the construction of the canonical family. The second part of the theorem says that given any entire graph, entire solution, when you look at its holomorphic quadratic differential that Abersh and I constructed, when you look at Q, then when you apply this construction here to get the two-parameter family, then the entire minimal graph is in the two-parameter family. Then it is in the canonical family of Q. And I'm going to say very rapidly, one of the basic tools used here is this theorem of Benoit-Daniel, which is the following. In space forms, in hypersurface and space forms, you know necessary and sufficient conditions that you can find an isometric immersion in codimension 1 into the space form, at least simply connected locally. And those two equations are the Gauss equation and the Cardassi equation. And they only depend on the metric and the second fundamental form. Benoit-Daniel found 4 equations which are necessary and sufficient to be able to embed a simply connected Riemannian surface together with a symmetric endomorphism A, the shape candidate for the shape operator, together with a vector field T locally, which is going to be the T we talked about, together with an angle function nu on the local surface sigma, into E of kappa tau. The first 2 equations are the Gauss equation and the Cardassi equation. The third and fourth equation are the necessary equations you get when you look at such an immersion into E of kappa tau, and you just calculate what the derivative of T is, delta xt, and you calculate what the differential of nu is. That gives you 2 other equations. And he proved that if these 4 equations are satisfied, then you have an isometric immersion of the surface sigma that you started with into the E of kappa tau, such that the T is the T we talked about and the nu is the angle function. Moreover, it's unique up to ambient isometry that preserves the vertical fibers. One beautiful application of this theorem he gave was a generalization of the Lawson correspondence in space forms. Which he called the sister correspondence. Theorem Benoit-Daniel. Consider a CMC sigma 1 with mean curvature H1 in E of kappa 1 tau 1. So I'm looking at simply connected. So it's simply connected piece of a surface of constant mean curvature H1. Then this corresponds isometrically to sigma 2 with mean curvature H2 in the homogeneous space E of kappa 2 tau 2 if and only if, first of all, kappa 1 minus 4 tau 1 squared is equal to kappa 2 minus 4 tau 2 squared. And secondly, h1 squared plus tau 1 squared is equal to h2 squared plus tau 2 squared. Let's look at this, what this means. Let's make a graph The vertical axis will represent kappa minus 4 tau squared. The horizontal kappa, the diagonal then, is tau is equal to 0. And each point in this plane represents an E of kappa tau. So I'm graphing E of kappa tau. And I want to see which E of kappa tau and surfaces correspond under this sister correspondence of Benoit. So if you're in this part of the plane, nothing, because this is minus 4 tau squared positive. So there's no E of kappa tau above the diagonal. On the diagonal here, we have tau is 0, kappa positive. So that is an S2 of kappa, two-sphere curvature kappa cross R. As we come down here, now tau is different from 0, and kappa is positive. So here we have a Berger sphere. And this is called a Berger sphere of the first type. You come down here, so kappa is positive, kappa minus 4 tau squared is 0, so we're in space form. Here, this is the three-sphere of curvature kappa. You come down further, and your tau is different from 0. Again, your Berger spheres, second type. Among all these homogeneous spaces, the only one where the geometry really changes with tau are the Berger spheres. That explains this type. Now, so let's go. Okay, so if I take a look at this theorem here, if I take a horizontal line, all points in this horizontal line represent kappa minus 4 tau squared as constant. So this equation is satisfied for all points on the horizontal line. So if you move along the horizontal line satisfying the second equation, you get isometric correspondences between the surfaces. So all I have to do, for example, is take a point here. For example, take a Berger sphere of the second type. Start moving to the left. Okay, things are going to change when I get here. What is this point here? So here, tau is different from 0, kappa is 0. Kappa 0, tau different from 0, that's Heisenberg space. That's Neal 3. That's Heisenberg space for this value of tau. Okay? So if I start off with an H1 surface here in a Berger sphere with a certain tau, and I start decreasing h and increasing tau, or vice versa, I get a surface that corresponds with isometrically in Heisenberg space. Now, if we chose tau equals a half here, that's normalization I was talking about. Let's keep on going to the left. I go here. What does this represent? This represents kappa negative, tau different from 0. That's PSL 2R tilde. PSL 2R tilde. Let's keep on going to get to this point. We get to this point, tau is 0. So that's H2 cross R. H2 of kappa cross R. So if kappa is equal to -1, say, and tau is 1/2, we have an isometric correspondence between Berger spheres, surfaces in Neal 3, and surfaces in H2 cross R. And you can check that the values are the following. Minimal in Heisenberg corresponds to H equals 1/2 in H2 cross R. Minimum in Heisenberg corresponds isometrically to H equals 1/2 in H2 cross R. This correspondence preserves the new angle function. So if you start off with the local graph to begin with, you end up with the local graph in the other space. So local graphs correspond to local graphs. Lawrence Houseworth, Joel Sprook, and myself proved that if you take a complete H equals 1/2 surface in H2 cross R, whose angle function does not change sign, then it is an entire graph overall of H2. Okay. Pablo and Isabel proved that under this isometric correspondence, that entire graph H equals 1/2 in H2 cross R goes to an entire minimal graph in Heisenberg space. Working very hard, putting all these things together, they managed to solve the Bernstein problem in Heisenberg space. Okay, I have 7 minutes left. I have a choice. Perhaps I'll talk about solve 3. Solve 3, I used to think solve 3 was a dirty word. I mean, really, many, many years, solve 3 was horrible. But it's a very beautiful space. Let me convince you that it's a beautiful space. Okay, what is solve 3? So, it's R3 with the metric, so I'll use coordinates x, y, s. The metric e to the 2s dx squared plus e to the minus 2s dy squared plus ds squared. That's the metric. So that's a 3-dimensional isometry group. And why is this interesting? Let's look at the surfaces y is equal to constant. Sigma y is equal to constant. Okay? What is that? That's e to the 2s dx squared plus ds squared. I claim that's the hyperbolic plane of curvature -1 in hierarchical coordinates. E to the 2s dx squared plus ds squared is equal to dt squared, dx squared plus dt squared over t squared, t positive, s equals minus log t. So this is hierarchical coordinates on the hyperbolic plane. It's totally geodesic. So we have a foliation by these planes, y is equal to constant. They're totally geodesic. And what does the S flow look like? The S flow, well, we know what that is. We take a geodesic here. This is S. The horocycles are the x coordinates. And flowing along S, we know it takes a horocycle here and contracts the length exponentially. So this is what we see on each plane sigma y, y is equal to constant. This family of planes has a fantastic property with respect to ambient isometries. They're invariant by symmetry. If I take x, y, s, and send it to x, 2y0 minus y, s, it's an isometry, an ambient isometry. Just look at the metric. So these planes y is equal to constant are invariant by symmetry, which is the Euclidean symmetry. It's an ambient isometry. The same thing is true for the planes x equals constant. Sigma x. They're totally geodesic. They're isometric to the hyperbolic plane, the curve which is -1. And what you're seeing are, so in this plane, again, we have the S flow. But now we're seeing horocycles. How am I going to draw these horocycles? I want to go back. Just take the same picture but turn the arrows around. S, S, Y. So now, flowing along the S direction exponentially expands the Y direction. So we have an anosor flow. This is an anosor flow. We have a stable manifold, unstable manifold. We have a splitting of the tangent bundle into these two-dimensional planes, each of them isometric to H2, invariant by symmetries. Now, when you have a foliation by planes, which are symmetry planes, you can do Alexander reflection. So you can prove that if you have an embedded CMC surface, one of the planes is the plane of symmetry of the surface. So you take sigma embedded in solve 3, h equals constant. So here's sigma. You start with these planes here. You start coming down, and you do the symmetry. The mean curvature vector goes up. You keep on going. You get a plane where it touches. You apply the maximum principle to say that's a symmetry plane because this is equal to that by the maximum principle. So your surface really doesn't look like I drew it. It looks like this with a symmetry plane. But that might have topology, right? It could be like this. But you have also the other family of planes orthogonal, sigma x. So come with sigma x here and do symmetry with these planes, and you realize that it's a sphere. So you have Alexandrov's theorem in solve 3. Any embedded compact constant mean curvature surface is homomorphic to S2. Homomorphic to S2. We do not have, one of the major problems in this subject right now is Alexandrov's theorem true in Heisenberg space? Is it true? Because in Heisenberg space, none of the planes are symmetry planes. So one has to find another proof that doesn't use Alexandrov reflection if one wants to prove that any compact embedded H surface in Heisenberg space is in fact a rotational sphere. We have Hopf's theorem in Heisenberg space. Any immersed sphere of constant mean curvature is a rotational embedded sphere. We do not have Alexandrov's theorem. Here in solve 3, where we don't have rotations, we have Alexandrov's theorem. Benoit Daniel and Pablo Mira this year wrote a beautiful paper partially proving Hopf's theorem in solve 3. So let me just state the theorem, and then I'll stop there. Let me just mention one thing that I forgot to mention. One of the reasons for studying constant mean curvature surfaces is the isoperimetric problem. You'd like to understand compact domains which bound the volume V, look at the area of the boundary of the domain, and you say it's an isoperimetric solution if that area is minimum among all possible areas bounding that same volume in your ambient space. So one of the major problems is to understand isoperimetric domains. One doesn't always have isoperimetric domains. If you take a catenoid in R3, it's a surface. There is no isoperimetric domain on a catenoid. Or any surface of negative curvature where the curvature is going to 0 at infinity, there are no isoperimetric domains. Why? If I take a small domain bounding a volume V and look at the area of its boundary, because the curvature is big negative, the area of the boundary will be much bigger if I drift off to infinity where it's getting curvature 0, bounding the same volume. So the thing that will minimize area bounding that volume drifts off to infinity. So one doesn't always have isoperimetric domains. However, if the space is homogeneous, then you always have isoperimetric domains. Of course, if you drift off to infinity, just pull it back by an isometry to a fixed point. Okay? So in these homogeneous spaces, you always have isoperimetric domains. One of the major problems in the subject is, what are the isoperimetric domains in Heisenberg space? Lots of people work on this. We don't know. However, there's a small contribution from the work of Abersh and me that says there exists a constant V positive such that if the volume in question is less than or equal to V, then an isoperimetric domain is a rotational sphere. It's bounded by a rotational sphere, it's a ball. So this does have an application to the isoperimetric problem. In Salve 3, one doesn't know much about the isoperimetric problem either. However, this theorem of Daniel and Pablo Mira is really pretty fantastic when you think about it. I'll explain why I think it's fantastic. Suppose sigma is an immersed H sphere in Salve 3 with H bigger than 1 over the square root of 3. Then sigma is embedded, unique, and exists. It's a strange statement, okay? The beginning of the statement is pretty simple to understand. It's embedded, okay? Immersed, embedded. Unique, that's also not too hard to understand. If you have two such, they differ by an ambient isometry. Exists, well, the amazing thing about this theorem is, since you have no rotations in the space, you have no way to construct examples of constant mean curvature. You know, in the other homogeneous spaces where we have rotations, we write down a differential equation, an ordinary differential equation. We solve the differential equation. We have examples of constant mean curvature. In Salve 3, no equation to write down. How do you construct examples? Well, the only way we know to construct examples in such a setting, geometric analysis, the Yeh techniques, etc. Okay, that works when you consider big values of H. And isoperimetric solutions. But we don't know isoperimetric solutions. We don't know that, etc., etc. So this theorem is amazing because it's proving unicity, it's proving existence and unicity without being able to construct these either by differential equations or solving an isoperimetric problem. This condition, h1 over the square root of 3, should not be necessary. This really, they work very hard to get rid of this condition. It certainly would be nice not to have that condition, but for the moment it's there. This condition comes up in lots of other problems. We're very embarrassed in the subject. We can't do it. I was going to talk about problems in the subject. I won't have time. But I'll talk about one problem because I can't help myself. It's a beautiful problem. Bill works on it a lot. I work on it a lot. understand stable surfaces in these homogeneous spaces, stable CMC, stable minimal. And in H2 cross R, we have a theorem that if the mean coverage is bigger than this 1 over square root of 3, then we know what stable H surfaces are. They don't exist. If H is less than or equal to 1/2, they do exist. The conjecture is, if H is bigger than 1/2, they don't exist. 1/2 is a good number. 1 over square root of 3 comes up there in H2 cross R2. 1 over square root of 3 comes up in lots of places where it shouldn't be. It should be a better constant, but we don't, the techniques we have don't manage to get that better constant. Okay, thank you very much. Let's go.